Hello viewers, I welcome you to our lesson today. I'm your online teacher, Mr. Steve Gitau, on our channel at Steve Gitau 3660. Today, we continue with our series of lessons that focus on the challenging areas in Form 2 chemistry. In particular, today I would like us to look at how you calculate the RAM of an isotope. Now, we shall do this via several different calculations, starting with the lowest order kind of a question, very simple one, and we progress to more challenging questions. This video is available on the platform alone and also on the playlist for the Form 2 chemistry. With that, welcome to the lesson. First and foremost, I would like us to look at what is an isotope. An isotope is that set of atoms of the same element having the same atomic number, that is, same number of protons, but different mass numbers, that is, having different number of neutrons. So you find that a common example of an isotope or an element that has isotopes is chlorine. It has the isotopes chlorine 35 and chlorine 37. That means the atoms in question here have the atomic number 17, but you find that the number of neutrons are different. With that, we look at how then do we calculate the RAM of such an element. You find that chlorine 35 occurs to the extent or has an abundance of 75%, while as chlorine 37 has an abundance of 25%. When we compute this one, and this is a common computation, we get that the RAM of chlorine is 35.5. So that is a common computation, and today I would like us to look at a similar question whereby we say, I read, an element P has two isotopes with mass numbers 40 and 42, whose percentage abundance is 60 and 40 respectively. That means the isotope with mass number 40 occurs in nature to an extent of 60%. The isotope with mass number 42 occurs in nature to an extent of 40%. So how is their RAM calculated? Viewers, I would like us to do this together, whereby we say that the RAM of P is therefore calculated as, we take the percentage, the first percentage, that is 60% times the mass number, that is 40, we compute that, plus we take the second percentage, which is 40%, multiplied by the mass number 42. And what does that give us? You find that viewers compute that from your calculator. 40% of 40 gives us, let's squeeze it here, it gives us 24 plus 40% of 42 gives us 16.8. And when we add the two, 24 added to 16.8, we get 40.8. So that is the RAM of the element P. It is important to note that usually the more abundant isotope has the RAM closer to it. In the sense we are saying 40 is very close to 40.8 compared to 42. 42 has a less abundance. So the isotope that occurs more in nature, that is with a higher percentage, takes the day, in the sense that the RAM of that compound is closer to its mass number. Viewers, that computation is very close to the one we have just highlighted on chlorine 35 and chlorine 37. So I would like us to look at question number 2. In question number 2, we are saying an element Q has two isotopes of mass number 60 and 62, whose occurrence in nature is in the ratio 2:3. Calculate the RAM of Q. So once more, we are seeing the occurrence being given in terms of a ratio, not as a fraction. However, the way we compute is the same. So the first item that we need to look at here is the total ratio. The total ratio here is 2 plus 3, giving us 5. So what does that ratio imply? It means the first isotope, which has a mass of 60, occurs 2/5, 2/5 in nature of all atoms of Q. The other isotope with mass number 62 occurs 3/5 of all the isotope atoms of Q. That means we move straight to the calculation, and you'll get that the RAM of Q is therefore equal to 2/5 multiplied by the mass number 60, and that gives us 2/5 times 60 plus the other isotope occurs to the level of 3/5 of 62. So viewers, get your calculator, compute that very quickly, and let's see what you get. 2/5 of 60 comes up to be 24. 3/5 of 62, we get 37.2. Now, compute that on your calculator. What is 24 added to that 7.2? And we get 61.2. Once more, I would like us to analyze. The RAM is closer to the mass number of which isotope? It is 61.2 is closer to 62 because of the higher percentage abundance compared to 60. So that concept is justified at this level. Let's move on to question number 3. It reads, an element M has two isotopes with relative abundance or abundances of 65 and 35. If the mass numbers of the isotopes are X and 31, respectively, find the value of X given that the RAM of M, element M, is 30. So in this case, we are required to find the mass number of one of the isotopes, and we have the RAM. So we shall work out in a similar version and compute what the value of X is. Now let's go to the question. We have the percentage, that is RAM of metal M, of element M, is 65%, and the first mass is unknown. As we take X, we add that to 35%, the second abundance in terms of percentage, multiplied by 31. And this one should give us a value 30. That is how we need to understand the question. The x is the unknown value here. So we may decide to work it two ways. The first one is multiply the root by 100 to remove the denominator of 100, or we can divide by 100 and we work out in decimals. Maybe viewers choose the approach that best suits you. I decide we take on the decimals. So 65 divided by 100 is equal to 0.65x added to 35 times 31 gives you 1085. 1085 all of 100, and that comes to be 10.85, and that is equal to 30. So at this level, we shift this onto this other side and we come and subtract. From 30, we subtract 10.85 and we get that 0.65x is equal to, when we subtract 30, when we subtract 10.85 from 30, we get 19.15. At this level, we divide both sides by 0.65 on both sides, 0.65, so that we get the x value. And our x value comes up to 4 decimal places to be 29.46. So viewers, that is how we look at, or we calculate for the unknown mass number. We're going to, you can pause on the video as we move on to question number 4. Viewers, welcome back. We look at now question number 4. In question number 4, we are having the question as the element lithium has 2 isotopes with the mass numbers 6 and 7. If the relative atomic mass of lithium is 6.94, determine the percentage abundance in each isotope. So viewers, I would like us to focus on the fact that in this question, the percentage abundance are not given. So how do we go about getting the percentage abundance? We have two methods which we can take this question, and let us look at method 1. Method 1. In method 1, we are going to use the idea of percentage abundance totaling to 100, such that if we let lithium 6 to be X percentage in terms of abundance, and we let lithium 7 to be in terms of percentage abundance Y percentage abundance, then you find that just like we have mentioned, 60%, 40%, 75%, 25%, the abundances add up to 100. So in a similar way, we develop the first equation, very simple, that x plus y will have to add up to 100. Whatever the percentage it will turn out to be. We are saying 60%, 40%, total is 100. 75% plus 25%, total is 100. So that is the first equation we can get from here. The other one is when we now look at the equation as we normally calculate it, that if we get x out of 100 multiplied by the mass number of 6, plus we get y out of 100, we multiply by the mass number of 7, that should give us 6.94. As we have been given in the question, that the mass numbers are 6 and 7 with unknown percentages, but the relative atomic mass is 6.94. So with that, it becomes very easy. The bit that we are left with here is just mathematical. We may decide to multiply throughout by 100. We multiply the whole equation, all the terms there, by 100. And what do we get? We get 6x plus 7y is equal to 694. Now we combine with this equation, the first equation, as x plus y is equal to 100. So this is the set or the pair of equations which we shall solve simultaneously. Now, we may decide to use elimination method. It is quite appropriate here. We use elimination method whereby we pick on x to be the item or to be the unknown to be eliminated by multiplying equation 2 by, we multiply this equation 2 by 6, and equation 1 we multiply by 1, meaning equation 1 remains unchanged. And that gives us 6x plus 7y is equal to 694. Equation 1 remains unchanged. We look at equation 2. We multiply each item by 6, and that gives us 6x plus 6y, and then 6 by 100 gives us 600. And these two equations we subtract so as to eliminate x, and that means 6x minus 6x is a 0, 7y minus 6y gives you 1y, and 694 subtract 600 gives you 94. That means y occurs at 94%. Then using this equation, which tells us that x plus y is equal to 100, what do? We substitute 94 for y. We have x plus 94 gives you 100. And that means what? It implies that x is 100 minus 94, and that comes to be 6%. Now, we need to show these percentages in terms of the elements. So I'll come here in this free space, and I can show that lithium 6 occurs, it is the one we had given the value of x, occurs to the tune of 6%, while lithium 7 occurs to the tune of 94%. Viewers, once more, it is important that we confirm the general principle that we had mentioned earlier, that the more abundant isotope has the RAM being very close to its mass number. 6.94 is closer to 7 and very far off from 6. That means the more abundant isotope has the RAM being closer to its mass number. Viewers, let us look at method 2. Method 2 is quite similar to method 1, but viewers may wish to look at it from that perspective. In method 2, we have only one proposition here, that if we let lithium maybe 6 to be X% in abundance, it occurs in nature to the level of X%, then automatically we are going to let the lithium 7 to be, like we have mentioned here, the total of 100. Then instead of y, we shall have 100 minus x, and that is going to be its percentage abundance. That means we need only one line of our calculation, whereby we take on the abundance of lithium 6 as x all over, that is x all over 100, we multiply by its mass number 6, and then we take on the abundance left, that is 100 minus x, all over 100, and that is the abundance multiplied by 7, the mass, the atomic number of lithium 7, and that should give us 6.94. So at this point, just like we had done in the previous working, we may decide to multiply throughout by 100. The entire working, both right hand side and left hand side, multiply by 100. When this 100 multiplies this one, we get 6x. This 100 and this one cancels out. We are left with 100 minus x into 7. We are adding this addition sign at that point. Then that comes to be this 6.94 multiplied by 100, 694. So we open up the brackets, then what do we get? We get 6x plus 700 minus 7 into x is negative 7x, and that gives us 694. Viewers, we put like terms together. 6x minus 7x is negative 1x, negative 1x. So we have negative 1x there. We add that to 700, and that gives us 694. So we put like terms together. We shift this onto this other side, and we shall subtract 700 from both sides. We subtract 700 from both sides, we get negative 1x is equal to 694, subtract 700, we get negative 6. We divide both sides by negative 1, and we get x to be equal to 6. The moment we get x is equal to 6, we now are able to get that 100 now minus 6 is equal to 94. And that means lithium 6 occurs to the tune of 6%, which is the value of x, and lithium 7, which we had given here, occurs to the tune of 94%. And viewers, that shows how well we are able to manipulate the values given under the calculations on RAM. I believe we are becoming very conversant now with the calculations provided here. I would like you to go over our discussion. Should you have a question, kindly post it on the remarks section, make a comment, do share the video, and subscribe so that every time I upload a new video, you will be the first one to be notified. Coming up next, we shall be looking at another topic that gives learners a challenge, and that is structure and body. In this topic, we shall examine on what is the relationship between structure and body, forms of structures which are generated by various bones, and the various compounds or substances that possess these bones. I look forward to meeting you in that lesson. Thank you for listening, and let's see you next time.